Then, okay, topology. Topology, we just need some basic thing. Open, close, compact. Okay, wrong. Should be bound, compact, and interior. Why we need this? Because later we talk about subdifferential, we will talk about relative interior, so that's why we need this. And also we know this, use this to define neighborhood. Then we can talk about calculus in n-dimensional space. Okay, then of course topology is saying that okay, you have a bunch of sets, okay, you have a bunch of collection of sets, okay, and then there are three sentences saying that if this three sentence is true for the intersection and union of these, then you have a topology and everything inside is open. Okay, that's the definition of topology, right? Again, I forgot the details. So if you want to go back, you go back. But I said we don't care about the details. So that means you need to know what's open and what's closed. So if a set is open, that means A belongs to some topology. That there are three sentences. Finite intersection is in the set, or union is in the set, and okay, an empty set and the whole set is in the set, something like that. Okay, and then what's closed? A is closed if A complement is open. That kind of thing. What's bounded? A set A is bounded if what there exists M such that what? Let's say I have some number telling how big is A, then this is bounded, right? Of course, M is smaller than positive infinity. If we talk about geometrical sense, I have something, this is my A, okay, doesn't not necessarily need to be convex set. I have M, is like I have a ball with a radius M that bigger than A, surrounding A, something like that. And then we almost forget what is open and closed used for, is for open ball and closed ball. So we will write B, CR, so what is this? BCR means ball at center C and radius R. So C is a vector in n-dimensional space, so it will be defined as what? Okay, let's draw a picture. So in R2, suppose C is 2, 1 and R is 3. Then you draw coordinate in classical sense, okay, not those are Artesian geometry or complex number. So 2, 1, right? 2 and 1, so this is IC, radius 3, so you draw a circle with a radius 3. Then this is the ball in two-dimensional space. Open means this line is not included. Close means this line is included. Okay, open will be R ball. Okay, that what we have this. Okay, it's like x minus c, the norm smaller than R. Close will be what? This thing, but this, right? We have a set of x, right? So open, this is strict. Close means we include it. Okay, and first we can also have what? A shell. Okay, shell or sphere is z equal. That means open is like this, right? Close is, this is close, okay? Shell is just this, right? And then, okay, just something next week, this is convex set, this is convex set, this is not convex set. So this is open, this is closed, this is shell, okay? This is convex, this is not. Because I put a point here, I put a point here, half of them is here, is not inside the set. But this is true for these two. Okay, anyway, this is later, not now, but this is the idea. Open, close, and shell. Okay, we have a ball. And then what? Because of this is also neighborhood. We write n, neighborhood. That means this is the epsilon delta thing in n dimension. So if I have a y that is in the neighborhood of x, it means y minus x is bounded by something, a number, let's say 5. That means any point distant to x smaller than 5, I call it neighborhood. And this thing can be generalized to call it distant, x, y. In this case, we are all talking about the classical Euclidean space, so it's 2 norm. But it's also possible, this is 1 norm. So now, with this, we talk about norm. Okay, norm. So L2 norm is just this, right? x1 squared plus x2 squared plus Pythagoras theorem, right? So then we also have 1 norm. 1 norm will be just absolute value. That means x1 plus x2 plus blah, blah, blah. And technically speaking, actually we also have absolute value here, but sin square we don't care. So the definition of p norm is absolute value xi power p, and then 1 over p, this. And there's an absolute value here. And then of course we also have this infinity norm. Infinity norm will be defined as the limit p go to infinity, which after some calculus argument, which I again forgot the detail and we don't care the detail, it will be the maximum element of what? Of all this. So just a recap. So suppose x is 7, negative 99. Then x2 norm will be what? 7 squared plus 99 squared this. x1 norm will be what? 7 plus 99. There's a negative here, don't forget. But we take absolute value, so we don't care about the negative sign. And then what about the infinity norm, it will be 99. Because there's a negative here, but we only care about absolute value, so the largest one is 99, so 99, something like that. And then there's a geometry. The geometry is, this is 2 norm, look like this. This is 1 norm, look like this. This is infinity norm, looks like this. So again, these are revision. I'm not going back to the details. Now we combine things. What does it mean? Combine things. I just talked about linear algebra. Now I'm talking about geometry. That means topology. Let's combine them. If I combine them, this is what? This is unit norm ball at center 0, radius 1, right? After linear transformation A, I get an ellipse. And then this major axis is the inverse of the eigenvalue of A. This is the second eigenvalue, right, of A. Let's say we have 2 eigenvalues, right? Then what about this? Well, it's the same, right? We will have, okay, I don't know, yeah, some, okay, my drawing is very bad, but you see my idea, right? And then this will be, okay, let's say this, okay? So this is A, this is what happens if I have A, I have this. So this is geometry. Now you may wonder, why am I talking about this? Of course, in later, it's very useful. For example, I want to minimize just norm square x, and let's say it's 2-dimensional. I can draw this thing and visualize it. This is just 2 dimensions, so that means it's x1 square plus x2 square root. But there's a square here, so I cancel it out, so it will be just x1 square plus x2 square divided by 2, right? And then if I plot it in 3D, it looks like something like this, right? Right? So this is a parabola, okay? This is x1, this is x2, this is the value, right? But what happens if I have an A here? If I have an A here, because of this argument, so I can draw something similar. So you imagine you stand here, you're flying in the sky, your eyeball is here, look like this, you see what? You see this circle, you see a bunch of circles. So if you are here, seeing here, what you see is a bunch of circles, okay? Now, if I put an A here, because of this argument, then what? You are also in the sky, look at here, now you will see a bunch of ellipses. Then you just draw this in this sense. So, okay, now it's very difficult, I'm not a good painter, but okay, how do I draw? Okay, you got the idea, right? And then, yeah. And then, yeah. Then this is what? This will be norm of AX something like this under some A for 2-dimensional case. Then with this in mind, actually then we can somehow use this to describe what happens in gradient descent in high-dimensional space. Okay? That's why I said this is useful. And this is also why I talk about topology now. Then what about this square thing? Well, it's the same, right? If I have this, then 2-dimensional case, it will be x1, x2. So, again, I'm in the sky, looking like this. I will see a bunch of diamonds that look like this. Then if I sit here, I will see diamond, right? So it's like this. Okay, I try my best to draw good picture, but you see my point, right? So you have this, and then you think inside is getting smaller. So this will be L1 norm cone, okay? And then what about infinity norm? Infinity norm is easy. It's just a box. It's just a box. So infinity norm is just this, yeah, something like this, okay? Infinity norm is easy. So therefore, this is the geometry. And then okay, once we talk about this, okay, this is a cone. This looks like a cone, right? This is also a cone. And then cone is useful because any direction cone is defined as any vector in this geometry cannot escape this thing if we scale it or we add them up. So this is a cone. And this is very useful because the set of gradient, okay, I should say this. In algorithm, we have this thing, the variable, the step size, the update direction. The set of D that makes function value go down is a cone. And then if we know how to characterize this, then we know how to select D. And once we have this together with how to select A, then we know how to design algorithm. And the geometry behind it is this kind of thing. It's exactly this kind of thing. Okay, I just tell you a little bit something later. So as long as the inner product between gradient and the D is negative, then this D are okay. This is the idea, but later, okay? Because today is revision. Okay, so now for topology, okay, we have closed and open. Bound is done. Bound is easy, like compact. Compact is closed and bounded. Okay, and this is a field. This is a Borel. I don't know how to spell anyway. Somebody proved this is the case. So basically, somebody proved that compact means closed and bounded. And this is very useful. We will use this 99% of the time. Why? Because when we talk about optimization, let's say I have this constraint set, we mostly will assume it's compact set. Why? Because this have no solution. Why? Because this is not compact. Let's examine it. This is number 9, this is R1. What's the feasible set? The set is any x larger than 3, right? So is, and this is 3. The problem is this part is open. So you are saying find the x that is as long as it's larger than 3, that this is small. Then one of you will pick, oh, I have 3.1. Then another person say, oh, why not this? And then you say, why not this? You see, this is the argument of the epsilon delta thing. Then you see this go forever. And since this is open, you can never reach 3, and you will have this as long as this is larger than 0. And since there's no smallest real number, Archimedean property in view analysis, so this problem cannot be solved. So therefore, this have no solution. But if you do this, then you have solution 3. But this means it's compact because you have bound. But if I don't draw it, it's open, this problem have no solution. And because of that, this is very important to know that for non-negative constraints, so let's say min fx, x larger than 0, this have no solution. You always need this, okay? And because of that, then here's a funny thing, remind you, this thing is open and closed at the same time, which is topology madness, okay? But anyway, we don't care, just revision, right? If this is closed, happy, okay? Okay, let me recap why I'm talking about this. I just show you that if I have optimization in open set, it have no solution. Then if I have optimization problem in this is open set. Oh no solution. We can never solve any optimization problem. But luckily, this is also closed. Done. So that means real number is an open set, yeah, but so what? It is closed. For this thing, we care about closed. We don't care about it's open. Then we have solution. Otherwise, we will have this issue. I just talked about it. This problem have no solution. You cannot give me a solution, right? So therefore, we always talk about compact. Compact means closer. And then, no, compact means closed and bound. Then what about bound? What about if we talk about closer set but it's not bound? If it's not bound, that means we can go to infinity. For example, min 3x, what's the value? This, because you don't have bound. So you go as small as you want. Then of course I go to infinity. Infinity is the smallest one. But if I have bound, that means x is larger than negative 5333. Okay? Then of course you cannot have this. Then the smallest one is this. Okay? That's the value. Because it's bound. That's the idea. Okay? So topology is just open, close, bound. These are quite trivial. This is not trivial because this is a theorem. And this theorem, the proof I think is very long. If you're talking about go to study topology at the professional level, but we don't care. We just say, oh, because this person proved that they are the same, then that's it. And for topology, there's also something called open cover, closed cover. We don't care. Okay? It's like, what is the compact? It's like this thing is covering this thing, is covering this thing, is covering this thing, and covering this thing, and then all of them have an intersection that's non-empty, blah, 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 which is topology thing. Okay, we don't need to go to that deep. And then what's interior? Okay, for interior, then we also have boundary. Okay? In topology, the boundary is also written like this, so it's a notation overload. Yeah, quite confusing because we will use this for subdifferential and subgradient. We also use this for partial derivative, and we also use this for boundary of a set. And if you're talking about calculus of variation, then this has other meaning. And then if you mix up other things like vector calculus, okay, then this is another thing. Oh my god, so many things. So be careful of this symbol. Now this is boundary. So basically it's this picture. So what is the boundary? The boundary will be basically just this, right? So boundary will be just A minus this. So this is the CLA, okay? The thing. A is the ball, okay? Oh, sorry, I made a mistake. Should be CLA minus A, okay? I made a mistake, yeah. Because this thing, subtract the yellow, is the black, okay? Not the opposite, okay? These are easy to understand, right? And then, so in this case, boundary is the shell, okay? So basically this, then what is the relative interior? Relative interior is basically the interior relative to something, relative to some space. So, suppose I have this, okay? We will call RELINT, relative interior. Interior is INT, okay? So, what's interior? I have a shape like this. This is my set S, okay? Interior of S is what? All the x in Rn such that what? This is x. This is my x, okay? The ball of center x with radius r is inside set S, not inside, subset. So it's like this. I can always find a ball here, then it's interior. Then what is the boundary? Boundary point will be using the same definition. This is the reason why we talk about open and close and ball. Will be what? Will be, well, just, right? Or you can say B, you can say part of the ball is in S and the other part, I call it BC, is not in S. So these are just definition. Again, if you forgot the detail, go back to the book. Now let's understand the meaning. So what is boundary? Boundary is, let's say we have a point here. Then if I draw a ball, part of this is inside the set and part of it is not. Then this is boundary. And if the whole ball is inside the set, of course it's inside. Then it's interior. That's the idea. Then you may then say, why we talk about this? Well, later we have to talk about this in the subdifferential. But now we haven't even started gradient descent, so that's why you don't need to worry about too much. And when we talk about relative interior, we will come back. And there are also some other applications. For example, we can also say that I just give you something next week or next week. It's like I want to minimize a multi-objective function, okay? Then if I update my point like this, suppose step size is 1, okay? Then the question will be, when will this D work? When will this D work? The idea is the Jacobian of this thing is a matrix, multiply D, the relative interior is non-empty. Then in the R plus, then the function will go down. That's why in this case we need this. But now we haven't even started what is gradient descent, so do not worry about this. When we talk about this, we come back. But now I'm talking about the basic math. That's why I will talk about all these things as a preview. Okay. So this is why we need. So let me recap. Okay, linear algebra, basic thing. Topology is what? Closed, open, and then we have ball, and then compact. Compact means closed and bound. Interior, boundary, and that's it. And we also have relative interior. Relative is something. Okay. Anything I miss? I think that's all for the topology. Yeah. And then continuous. Yeah, almost forgot. What is continuous function? Okay, there are two definitions. One is from calculus and one is from topology. I use the one from topology. Basically, is that you have a bijective map. You have a bijective map between two sets. So F is a set A and B. So you have an A, you have a B. So injective means this, by surjective means everything in B is mapped, right? So then if these two cases is true, then you have a bijective map. And if this F is a bijective between A and B, we call this continuous, because we can have inverse. And if this is open set, then this is also open set. That's the definition of topology thing. Again, these are details. We don't need to care about too much, but just remind you we may need this. And this is open set and continuity. Again, these are very quick go through of the revision. Now, calculus.